So for Stokes' theorem, we're going to have to use surfaces, and part of it is to look at the boundary of a surface, so we need to define what that means and explore that a little bit. For some surfaces, it's going to be pretty straightforward what the boundary of a surface looks like. Let's say that we're in R3, x, y, and z, and let's say our surface looks like a magic carpet, right? It's some function that's up, some wiggly function up here. And the boundary of the surface is just going to be the outside edge of this surface. So you could think about taking the outside part of this carpet, and that's going to be, I don't know, I guess I drew it black, because that's how I represented the surface, right? That's going to be this green surface, right? The edge. That's because that's a pretty easy surface to look at. Let's say that we have something that's a little bit more challenging. Let's say that I have a cylinder. So it's just the hollow cylinder, it's not filled in, it doesn't have any caps. And I'm asking, what is the boundary of this surface? It's like a sheet that's been all rolled up, right? For this surface, it actually has two different boundaries. It has this circular boundary up here up top, and it has this circular boundary down here at the bottom of it, because it's a hollow sheet that's been rolled up, and those are going to be each of the edges. How do I decide that it's the boundary of the surface? It's where I bridge from the outside of the surface to the inside of the surface, and any of those holes are going to be what we call our boundaries. So similarly, if I have something like a cone, what's the boundary of this cone? It's just going to be this part of the cone. It's not going to be the very tip, because you can't get into the inside of that tip. There's no hole there. So any place where there's no hole, that's not going to be a boundary. And then in my final example, this is the one I think is most complicated in some ways. Let's say that I have a sphere, like a sphere of radius 1 or something like that. Like, where's the boundary of this surface? Like, I sort of want to trace along the edge, or maybe I want to trace along this circle, but really there's no way that I could get from the inside of this surface to the outside of the surface. That this is a surface with no boundary. Because it's like we've taken this cone or something and we've closed it up. Like, what would have been this boundary has been all pinched together, and there are no holes. So this is, we also call a closed surface. Because there are no holes or ways to get from one side to the other. So I promised you that we'd talk about boundaries of surface. Let's also talk about orientation of those boundaries. So to define the orientation of a boundary of the surface, I want us to recall what we saw back in R2. And this is my little recall. We'll put a little thought bubble around it, because if we're just in the xy plane, and I have some surface, usually when we're in the xy plane we don't call these surfaces anymore, we call these regions. So we have some region, and we talked about the orientation of this region, and we knew that to apply Green's theorem, it always needed to be positively oriented, which meant that we always had to turn in a counterclockwise way. So positive orientation, it means that our boundary needs to be closed, and it needs to have counterclockwise . And this goes along with our right-hand rule that if I'm turning along this counterclockwise, that using my right hand, my thumb should be pointing positively. It should be pointing up. So that's what we saw when we were just in the xy plane. And we want to take this idea and expand it to the boundaries of these surfaces that are in 3 dimensions. So let's take a look at the boundary of this surface. I want to make sure that the boundary is positively oriented. So as I travel along this boundary, should I travel this direction or should I travel the other direction? And the same sort of idea, the thinking applies. The problem is, it's not so straightforward which way counterclockwise is anymore, because maybe this is relatively flat, but let's say it was really tilty or somehow in opposite orientations, that it really matters which way the normal vector is pointing. So once I determine, let's say that in this case we have an upward pointing normal vector. And that's standard. In general, we like to parameterize our surfaces so that they have an upward pointing normal vector. And now I can use my right-hand rule, making sure that my thumb is pointing in the direction of the normal vector. I'm going to walk around this path in a way that is counterclockwise. So let's put our little turtle, this is my little turtle. He's going to be on the top of the surface and he's going to walk along the edge. He knows it's the top of the surface because the normal vector is pointing up in this case. And so as our little turtle walks along the surface, the region is always going to stay to his left. So I wrote that in red. So as the turtle's walking, his left-hand side is over here, and he's going to walk this way along the surface. And that means that the boundary should be oriented this way in order to give us positive orientation. Let's look at one that's a little bit more complicated. So let's say that here's our cylinder, and we have an outward pointing normal vector. I'll draw in a couple of the normal vectors because that to me is helpful, saying that no matter where I'm at, these are going to be our outward pointing normal vector. And so now, as the turtle is walking along this surface, we know that we need to make sure that the boundary stays to his left. So as he's walking along the top here, if I'm thinking about this outward pointing normal vector, my right-hand rule is hard to visualize. What does this mean? Because it's not flat the way that this was flat. So I'm going to draw in my turtle, and I know that if the turtle is on the top of the surface, here's my turtle, that the boundary needs to stay, or the surface needs to stay to the left. So in order for my little turtle, here he has a tail, now he's a turtle, as he walks around this outer boundary with the normal vector pointing up, which he is, the region has to stay to his left. So in this case, he's going to have to walk in this direction. And that's going to give me a positive orientation. I wrote it in red over there, so I'll write it in red over here. That's going to give me a positive orientation on this boundary. But let's see what happens when the turtle is down here. When the turtle is down here, I'm going to erase that side, that's sort of the back side. Right? Again, the boundary has to stay to the left. The boundary. I keep saying it incorrectly, and I apologize. The surface, the region, the flat part has to stay to the left. So as the turtle's walking, it means that his left-hand side, which in this case, this is left, has to be where the surface is. And so that means that he has to walk in the opposite direction. So a positive orientation, in this case, means that the turtle walks that direction. Finally, let's take a look at this cylinder, and we're going to do the same thing. We're going to have an outward pointing normal vector. That's something that's standard. And if our normal vector is pointing out like this, it means that the turtle is going to be walking around the outside, and we want the surface to stay to the left, so our turtle is going to have to walk this way. And finally, there's no boundary, so we can't talk about the orientation of this boundary for the cylinder.